My name is Nick Lariviere, and I'm a member of our kernel development team, and I'm going to talk a little bit today about working with large data sets in Mathematica. And so we're going to cover four main topic areas, just a sort of brief introduction about what I mean when we talk about big data and what sort of formats and functions we're looking at. Then we'll look at some speed and memory performance benchmarks, look at some tips and tricks and strategies for working with big data, and then finally talk about some future improvements we're going to be making in Mathematica version 9. So the first real question is, what is big data? There are a lot of different definitions of big data in software technology, but for the purposes of this talk, I'm referring to big data as primarily numerical data sets, though we'll also look at some examples that involve strings for time series and things like that, that push the physical memory limits of your machine. So working with files that take 2 gigabytes or 4 gigabytes or 700 gigabytes of memory to keep in memory, and some of the strategies that exist. So I've got just some examples looking at some tabular real values, some financial time series data, or some log information here. All of these are data types that you'll oftentimes run into that fall into this category. So the first thing is to get a measure of what functions and formats are used for loading data into Mathematica. And I've broken them down into four main functional areas. Import is probably the function that everyone's most familiar with. It has some nice advantages. It's very user-friendly. It supports a wide variety of formats, and basically you say import this file and import figures it out. The downside is there's a cost associated with that user-friendly nature, and that generally means you're going to have a relatively high amount of memory overhead and relatively long load times, because import needs to be able to facilitate arbitrary data formats and figure out something reasonable to do with them. Read list is generally the next function that people get familiar with. It has the advantage of being fast relative to import. It's very flexible. You can control the types that are imported, whereas import itself generally tries to auto-detect types, and it also has support for streams, something that import isn't as robust with. The downsides are it's not quite as user-friendly, and it works best only with plain text data formats. Binary read list is the next function you'll probably run into, and it has better performance than either read list or import, but it generally ends up being the least user-friendly function to work with, and it can involve a lot of data processing, particularly if you're not working with binary data formats. The last one that many people aren't aware of is using get to load data, and specifically using it in conjunction with dump save. The two biggest benefits of using get is that it's the most efficient loading operation, and it preserves packed arrays, which can substantially increase the speed of loading. The downsides is that the files first need to be loaded by another mechanism so that they can be reloaded with get, and those file formats, because they're essentially a binary dump, aren't transferable between platforms or architecture. Also, briefly looking at, these are the data formats that we've identified as being friendly for working with big data. They're all either plain text data formats or binary data formats, and this is useful because they require the least amount of processing. You don't see XLS on here, for example, because the proprietary binary format they use, along with the XML base for it, requires a substantial amount of processing, and in Mathematica's case uses another converter. So there's a whole extra step involved. All of these data formats are actually parsed directly by Mathematica, and so we remove that extra complication of having a converter in place. So let's look at a couple of memory benchmarks. I'll just start off here by starting with a fresh kernel session, so you know I'm not stacking the deck. And I'll also start by setting the history length to 0, which prevents any previous evaluations from stacking up and throwing off our results here. So I'll pull out a sample data file here and take a benchmark for what the memory in use is. And we can look and see this is slightly under 2 megabytes in file size. I'll start by looking at read list, and we can see it takes about 0.17 seconds and about 5 megabytes of memory overhead, which isn't terrible considering the file size. If we then look at import, we can see that it takes substantially longer and more memory to use. And this is primarily because of the extra parsing that import has to do. Now, just to extend that a little bit, here is a simple breakdown of using the same sort of data format, comparing read list and import. And you can see as the number of records increases, there is a more substantial increase in overhead for import than there is for read list. And this happens because of the way that import's set up. It's having to parse through all of that data in one entire block, figure out what the data is, and then go through sequentially and re-engineer the file. So, there's not a big timing difference between these, even with 20,000 records, but as you extend this up into the area of working with 1 million records, that data overhead starts to become a problem. So let's look at the same sort of benchmark here, looking at read list versus binary read list. In this case, I'm just going to look at timing here, and we can see that there's a substantial difference in the timing here. You may also notice that in this case, they're reading 2 different data files. It's the same data, which we can see down here, but in the case of binary read list, it's actually been saved as a binary data format. And here again, we can see there's a substantial difference in the amount of memory overhead associated with reading files in binary. In this case, it's 100,000 records, and binary read list has almost no increase in memory over the in timing over the baseline amount of timing required. So beyond just looking at the number of records that are in a file, dimensionality also has an important part of working with big data. The longer a data set is in any one dimension, the more difficult it is to process. Whereas a more square array is going to process faster. And that has to do with the way that expressions are built up in Mathematica. And we've got some benchmark information here, but to make that a little bit easier to visualize, here is a bar chart showing the same data. It's 4.68 million elements that are real numbers between 0 and 10. The only difference being this data set is arranged in about 230,000 by 200 of an array, whereas this is a unidimensional array. There's not a big difference in timing between read list in these cases, but import, you can see there's a substantial difference, and that again has to do with the way that it processes the data. But the more regular your array is, the more square its dimensions are, the faster and the less processing that's going to be involved in loading it. So we've got some basic ideas for what the benchmarks are for loading data in with these different functions. Binary read list is going to be faster than read list. But how do we actually put that to use? And one of the things that I'll be talking about a little bit throughout the rest of the presentation is the difference between prototyping, where import's really easy. You just say, I'm importing my data file, or I'm importing part of it. But when I go to a production environment, or I'm working on optimizing my code, it's not as efficient, and so I need to take the extra time to actually work out a way of optimizing that. And one of the ways of doing that is making a helper function. So in this case, I'll look at an example financial time series file that's included with Mathematica. It's very small, but just for a benchmark, we can look and see it takes import just a little bit of time to read this in. And we know from the previous examples that read list generally has better timing associated with it. So here's a small helper function. All we're doing is reading in the values and indicating that in addition to normal record separators, we're also looking for commas. And then we're running toExpression over the final result to make sure that the results match up with what import has. And in this case, because the file is so small, there's negligible timing. But we can see that the results are actually the same. And if we extend this up along the same sort of format, here we're reading in that data, and we can see that there is a substantial time savings here. The slope is much shallower for this read time series function than import. And without doing a whole lot of work, we're able to actually customize this. Another thing we can do when we're building this time series data with a customized function is, in this case, we're just pulling in the string, but we can actually run datelist on this file, and then it takes longer to import, but if we look at the elements here, we're actually reading those into a list. So we can do additional processing as part of the loading operation and streamline some of the work that we're going to be doing farther down the pipeline. Another strategy deals with working with files that are beyond your physical memory capabilities to load into Mathematica. I have 8 gigabytes of RAM on this machine, but if I want to read a 16 gigabyte data file, there's no way that I can physically load that all into memory. There are different techniques available for working around that, and one of them that's available when you work with data streams is to only read in part of the file. It's very rare the case that you're going to have a data file that is made up of numbers that you need to look at in totality for any one given operation. So we can use strategies like opening a stream connection. In this case, I'm just pulling in part of that same time series file, and we can see that the stream opens to a 0 position to begin with. But we can use a function like find to select a specific record, and we can see then that the stream position is adjusted. And if we use read list on that stream with its current position, we can then read in subsequent elements based on whatever our loading operation specifications are. And that would give the same sort of operation. Again, this is a trivially small file, but we can run the same sort of operation on data files that are terabytes in footprint. The next strategy has to do with a function I mentioned earlier, reading in previously loaded data using get. So in this case, I'm going to look at the timing of importing this function versus actually reading in a reloaded version. So in this case, I've loaded the data into the variable data. I'm going to dump save it and then remove that definition. So if I ask for the dimensions of data, it is undefined at this point. I'll then clear the system cache to make sure we're not doing any sort of optimization where we're saving this information again. And we can see that we're orders of magnitude faster, and we're preserving the data footprint itself here. Again, we have some benchmarks here. Note that when we do load in this dump save data, it maintains a packed array, so that if we have a large data file that's been optimized to in memory in Mathematica, it's a sparse array, or it's an array constructed entirely of reals or something of that nature. If we dump save that file, we don't unpack it to save it, and when we reload it, it maintains its packed behavior so that we have a smaller memory footprint and there's less processing. There aren't any other mechanisms that exist in Mathematica that preserve that packed array structure using save in a plain text format, read list, binary read list, import. All of those require unpacking and repacking the array. And just to get a visual cue as far as total memory overhead and timing here, you can see that there's a substantial difference working on this data file that is 585,000 by 8. The read timing is essentially 0 with get, and our memory overhead is also essentially at the value of the packed size of the array. So we have a 1-to-1 import overhead to expression size ratio, which is very hard to achieve by any other means. So let's talk a little bit about some of the future improvements. In some of the other talks during the conference, you may have heard mention of either the 64-bit minting for the version 9 kernel, or that the 2 gigabyte expression limit has been removed. As of version 9 and forward, the way that Mathematica internally handles expressions has been changed over from a partially 32-bit representation using pointers and other things to a true 64-bit representation. That means that it takes a little bit more memory, but you essentially have 2 to the 64th bytes of physical storage available. So Mathematica can load in arbitrarily large files. There are no physical systems that exist in the world right now that will exceed its ability to load into memory. And just as an example here, to my knowledge, this is the largest data file that's ever been loaded into Mathematica in history, because this technology hasn't existed outside of Wolfram, and we don't have any computers that are bigger than this. This is a 15 billion element 64-bit floating point array in a one-dimensional list, and the file size is 111 gigabytes, which it actually took substantially more time to create this file and to move it over into a location that was readable than it did to load into Mathematica. In this case, we're looking at about 13, 14 minutes to actually load the data file in. And in this case, I skipped unpacking it because that probably would have pulled our server down since we didn't have enough memory available, which is something we found out a little bit during testing. It takes a long time to write 2 terabytes worth of paging files into memory. And again, we're looking at essentially 0 overhead other than the expression size. We've also taken some observations from this project looking at the performance of read list, import, binary read list, and made some improvements. Here I've just got a bar chart showing the differences in timing between a number of different data files. A lot of these are based off of real-world files that we've had people present to us in the past. So these include numbers in scientific notation. There are sparse arrays in there. Some of these are really dense arrays. And you can see that there's a substantial difference in timing between version 9 and version 8. Universally, it's gotten faster. And in some cases, we're 3 to 4 times as fast as we were in version 8. And it's always a goal with Wolfram Research not only to bring new innovations forward in Mathematica, but also to improve existing technologies so that we can take this sort of improvement is going to universally increase performance for Mathematica users. This improves not only the performance of read list, but import as well, which is built out of read list, and should also decrease the amount of processing that's required. There is a slight trade-off with the 64-bit minted kernel. It does take more memory to hold these numbers, but that amount of overhead is very, very minimal. It's something on the order of about 15%. And also, there isn't a lot of time to go over a lot of the things that we've found during this project, during the talk today. So one of the things we've also done is, surprisingly enough, there previously haven't been any tutorials in Mathematica about loading in data. We have tutorials on import and how different formats are affected, but we don't really have anything that breaks down how to work with data and what the different options are. So that's something that we've spent a lot of time putting together. It includes a number of things that we unfortunately couldn't really cover in this format. Things like how to monitor your memory usage. There are a couple of things you need to keep in mind. For example, byte count isn't a good way to estimate how large an expression is because it takes some shortcuts. It's a pretty good snapshot that's very fast, but you don't want a 100 gigabyte data file. If you ask for the byte count, you don't want it to crawl through the entire expression tree and tally up all the results. So we've tried to outline some things that give you a good idea of how to monitor your memory usage and ways that you can improve it. And also some more advanced topics like using binary read list on files that aren't natively binary. So reading ASCII files in and how you actually process that out. And again, just sort of a summary of what we've covered here. For fundamentals, you want to make sure you pick the right function and the right format for reading your data in. You want to be mindful that not only the amount of data and the file size of your data file are important, but also the dimensionality of it. And to make sure you aren't shooting yourself in the foot with something like caching all of your previous evaluations. Writing Helper functions using get and dump save are great ways, especially in production code when you're going to regularly be reloading a set number of files. Those are easy ways to optimize your code, and also look for these sorts of improvements with the new kernel in Mathematica 9, along with the tutorial that we'll be introducing to try and improve our knowledge base for working with loaded data. Thank you, everyone, and hope it was a helpful talk.